Hello, fabulous AP Calculus students. Today we are going to determine infinite limits and we're going to figure out their relationships with graphs. Afterwards, we'll briefly discuss the intermediate value theorem. So for today's lesson preview, you use concepts from limits and continuity in order to graph your functions. There's a different answer for each one of your sketches. So if you'd like to clarify or check on your answer, just let me know. For question number 3, you use numerical data. So as you were approaching 2 from the left-hand side, you saw that the y values were getting infinitely small. They were going towards negative infinity. On the right-hand side of 2, your y values were getting infinitely large, so they were going to positive infinity. From our last discussion, you know then that the limit as x approaches 2 does not exist. Matter of fact, I'm pretty certain that f of 2 does not exist either. And if f of 2 doesn't exist, is f of x continuous everywhere? And the answer to that should probably be no. For today's lesson, we're looking for infinite limits. Now, generally, a limit that goes to infinity will happen at a vertical asymptote. It doesn't always have to be a vertical asymptote, but that's what we're going to look for most often. So a limit that increases or decreases without bound is called an infinite limit. So as we look at our graph, because we want to associate graphs with our analysis, we're approaching -1 from the right. So let's see here. We're approaching -1. The graph is going up, 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 up. So that is positive infinity. So as we're approaching -1 from the left side, our graph tends to be heading downward. So that would be negative infinity. So in answer to the question, what is the limit as x goes to -1? That, of course, does not exist. So we can tell graphically that at a vertical asymptote, this one has infinite limits. But let's look at the function itself, because we don't want to have a graph each time. 1 over 2 times your x plus 1. When we're talking about limits, of course, you try substitution first. If you substitute -1 into your function, f of -1 seems to have 1 over 0. And if you have a 1 over 0, that's your clue that there's a vertical asymptote at the value that you're substituting. If you have 0 over 0, you might have a removable discontinuity. But f of x in this case has a vertical asymptote at x equals -1. And please remember that when I ask you where a vertical asymptote occurs, write the equation. Now, when we look at question number 2, look, no graph, you knew that was going to happen, didn't you? But let's see what happens. If I take the limit as x goes to -1 and I try substitution, f of -1, when I substitute, is 2 over 0. That's my clue. So if I have a number divided by 0, there must be a vertical asymptote at -1, so at x equals -1. But you know how to factor. When you look at your denominator, the factors of x squared minus 1 give you the factors x minus 1 and x plus 1. So you're going to have 2 vertical asymptotes, both of them occurring at positive and -1. All right, now, you know you have vertical asymptotes. So that tells you that your answer as you approach an asymptote is either going to be positive or negative infinity. So you've got to figure out which one. So after you substitute to determine that you have a vertical asymptote, next you're going to do a sign analysis. The sign analysis will tell us whether or not we are going towards positive or negative infinity. So let's try to figure this one out with a sign analysis. As we approach -1 from the right, think about a number line for a moment, if you would. And on my number line, I'm going to put -1. I might as well put 0. Here's 1, just because we know that 1's also important in this problem. So to the right of -1 places me in this part of my function. If I were to think about some number to the right of -1, I might think of -0.9. To do your sign analysis, take -0.9, substitute it into your function. So f of negative 0.9, I really don't care about the answer. What I care about is whether it's positive or negative. You take your negative and square it, add 1, it's a positive. You take your negative and square it, and then subtract 1, you get a negative. So a positive divided by a negative is a negative. Now remember, we already established this was at an asymptote, so negative infinity. To the right side of negative 1, your asymptote is, you're heading down the asymptote. Oh, to the left side of negative 1. So think about the left side now. On the left side of negative 1, negative 1.1 would be a good place to think about our functions. We have f of negative 1.1, and this is all in your mind, or you can write it out. That's totally up to you. When you put negative 1.1 in the numerator, you get a positive, and in the denominator, you also get a positive. So on the left side of negative 1, you're going to get a positive infinity. Now, as you look at x approaches negative 1, you notice that the answers are different on either side, so this answer does not exist. So one side of the asymptote, you're heading upward, the other side, the function is heading downward. All right, let's see what happens to the right side of 0.1. So on the right side of 0.1, let's use 1.1. F of 1.1, doing a sign analysis again. For 1.1, and the numerator is positive. Substituting in 1.1 for your denominator, it's positive. So you're going to have positive infinity, because at a vertical asymptote, you're either going to go up the asymptote or down the asymptote. All right, now we're looking at 1 from the left. You know what? Let's use positive 0.9 this time. So positive 0.9. And when I find f at 0.9 using a sign analysis, it is positive over a negative, which tells us we will head down the asymptote. So now, algebraically, we can figure out whether or not the vertical asymptotes are positive infinity or negative infinity when we look at limits. So for example, 3, let's see here, g of x is negative 7 over x minus 3 squared. So I'm looking for the limit as x approaches 3. Now, obviously, we have to do the left side and the right side. When you substitute 3 in, g at 3, you have a number divided by 0. And remember how I said we're not allowed to write that? Well, that's still true. You have an indeterminate form. Therefore, you must have a vertical asymptote at x equals 3, because you try to divide by 0. All right, so if you try to divide by 0, you definitely have a vertical asymptote. So now we're going to do a sign analysis. On the answer has to be positive or negative infinity. It might not even exist because we're doing both sides. Let's see here. Thinking about 3, to the right of 3, let's use 3.1. Yes, I'm real original there. To the left of 3, use 2.9. So g at 2.9 is going to be a negative over a positive, which of course is negative infinity. And then g at 3.1 is a negative over a positive, which is negative infinity. So both the right side and the left side are going to negative infinity. So the limit for this one does exist, even though it's a vertical asymptote, and that limit is negative infinity. You've been using the words vertical asymptote for several years now, but the definition actually involves the idea of limits. So as if f of x is approaching infinity or negative infinity, as x approaches some value of c from the right or the left, then x equals c is a vertical asymptote. And you recognize your vertical asymptote by allowing your denominator to equal 0. Now, be aware, sometimes when your denominator equals 0, you might have a removable discontinuity. You do need to be on the lookout for that. For example 4, we bring our trig functions back into play, and we want to determine where f of x has a vertical asymptote. In order to figure that out, let's rewrite the cotangent of x as our cosine of x divided by the sine of x. So So when we look at f of x now, we know that vertical asymptotes are going to occur where the sign of x is equal to 0. And understanding our unit circle trig tells us that x is going to be equal to several values, 0, plus and minus pi, plus and minus 2 pi, and lots more. So what we're going to write is that the vertical asymptotes will occur at x equals some value of k times pi, where k is equal to 0, plus or minus 1, plus or minus 2, and it goes on. So all the vertical asymptotes can be found using this nice little pattern, x equals k pi. For example 5, I want you to think briefly about each of these problems. Before I review example 5, I want you to take 5 minutes and give these 4 questions a try. Stop the video now, restart when you're ready. Perhaps the first question is easier to think about if you write the limit as x goes to infinity. You have x squared plus 1 over x squared. In that case, you can easily see that there's a vertical asymptote at x equals 0. Now, does this problem go to positive infinity or negative infinity? If you think about the limit as x approaches 0 from the left of our function, or call it f of x, what you should notice is if you chose a negative value, so let's say negative 0.1, you have a negative over a positive, a positive over a positive, which is always positive. So it's heading to positive infinity. And the limit as x goes to 0 from the right-hand side of f of x, if you put a positive again over a positive, it's heading towards positive infinity. So for question A, your vertical, as you approach 0 from both sides, you're going to positive infinity. Now question B is a little bit more troublesome. However, you're an awesome student and you tried substitution first. So when you tried substitution first, you came up with 2 over the cotangent of pi. Now, perhaps you had to think about the cotangent of pi for a minute. And if you did, you would understand that the cotangent of pi is just going to be equal to the 2 times the sine of pi over the cosine of pi. Now maybe that's easier for you to think about. The sine of pi is 0 and the cosine of pi is 1, so this is negative 1. So this problem is actually not going to have a vertical asymptote at 1, and the answer is 0. Now for question C, you're approaching 0. So perhaps you rewrote your problem. You have the limit as x approaches 0 from the right, 3 cosine x over sine of x. Now, 0 from the right. I like to think of the unit circle for a minute. And if you're approaching 0 from the right, what does that mean in your unit circle? That means perhaps you are approaching from pi over 6. And you know that pi over 6 gives you a positive for both the sine and the cosine. So your answer is positive infinity. And if you are approaching from the other side, you're going to also have a, though it doesn't matter now, does it? Because we were approaching from the right. Now, question D, you're approaching 0 from the left. So perhaps you followed the similar idea. Rewrote this as x approaches 0 from the left, x cubed plus 1 over x. Now, you know your answer is going to be some sort of infinity. You have to figure out which one. Perhaps you did a sign analysis, this time choosing 0.1. And if you choose 0.1, you end up with a positive, can't choose 0.1, we have to choose negative 0.1, and that would give me a positive over a negative, which would be negative infinity. And now it's your turn to practice again. For today's lesson practice, you have 20 minutes and only 20 minutes. Set a timer. If you don't finish them all, it's really okay. Spend 20 minutes on the next part of the assignment, and then you can check some answers once you're ready. Stop the video now. So once again, you're being reminded how to use your calculator to fill in a table of values. So make sure you take advantage of that opportunity and actually fill these in to come up with the correct answers. Numbers 14, 16, 18, 20, you should be pretty good at. Make certain that you can factor number 20. You would see a removable discontinuity there. Number 22, you're going to have to do some factor by grouping in order to determine which factors are removable discontinuities and which ones are vertical asymptotes. Same thing with number 24. 26, so we're going to look at a little bit more closely. Think about where your cosine pi x is equal to 0. And what I do is take the angle pi x and set it equal to all the values that would give me the 0. Then I divide by pi so that I get my x is equal to 1/2, 3/2, 5/2. Once you've established a pattern, notice that these are all increasing by 1 as we go forward. We write 1/2 plus k. You can also use the variable n. It's generally k or n, where k is equal to 0 plus or minus 1 plus or minus 2. Now, 28, that is a sneaky little problem. So it follows the same idea of what's going on with number 26, but it has a removable discontinuity. You were not fooled. You knew not to include 0 in your k values because 0 actually has an answer. Remember, the limit will go to 1. So removable discontinuity, therefore it is not a vertical asymptote. So excellent work on that. You guys are doing a great job. So check through your answers on this page. Number 32 was the sneaky one. So as we are looking at -1, remember, if you were to rewrite this problem as a limit problem, the limit as x approaches -1 for the sine of x plus 1 over x plus 1, you actually have that fancy function, sine of the angle over the angle, where the angle is heading to 0, so the answer would be 1. Therefore, this is a removable discontinuity at x equals -1. So the intermediate value theorem, one of those hot topics on the AP Calculus exam. Let's take a close look at it. Informally, here's what we have. We have 2 points connected by a continuous curve, and that is the clue. We have to have a continuous curve. One point is below the other point. So if we were to follow that continuous curve from one point to the next, somewhere along the way, we had to go hit a point that was between them. All right. There is at least one place where the curve crosses a line that was between points A and B. Of course there is. You knew that. I knew that. That is its own math theorem. Now, the formal way to look at the intermediate value theorem. So we have a function, f of x, that is continuous on a closed interval. So those two pieces are incredibly important, continuous and closed. And f of a, of course, is not equal to f of b. And k is any number in between those y values. Then there is at least one number, notice the words at least, one number c in ab such that f of c equals k. So we now have an understanding of the formal definition so that we can look at our example 6. So for example 6, we're going to use the intermediate value theorem to show that our polynomial function f of x has at least one zero on the interval 0, 1. In order to do that, first we need to consider, is f of x continuous? Make a statement. F of x is continuous on 0, 1. Now you might wonder why, but isn't f of x a polynomial? And this polynomial has no domain restriction, therefore it's continuous. The next thing we want to do is look at our endpoints. F at 0 is going to be equal to -1. And f at 1, when you substitute, is going to give you 1 plus 2 minus 1 is equal to 2. So when we look at the formal definition, we have f is continuous, got it. It's on the closed interval, got it. We know that f at a and f at a is not equal to f at b, we know this. Then there must be one number c between a and b such that f of c is a value in between. So what we know is that -1 is less than or equal to 0, is less than or equal to 2. So there must be at least one 0 on AB, and AB in this case being 0, 1. And now for good measure, we write by the intermediate value theorem. The cool people call it the IVT. So for this lesson, you have 2 more problems to consider using your intermediate value theorem. So take a few minutes, complete the rest of this lesson. You have worked hard today, most definitely. We got a little bit technical with some of the problems we were working on. So on page 88, I have a series of problems for you. Make sure once again that you're working on multiples of 3. If you prefer the odds, that's fine. Just get some good practice. The intermediate value theorem is on page 80. So also take a look at those questions. You're doing a great job. I'm really proud of you. So you have an excellent day.